Hello, everyone. My name is Will Beebe, and for our week on habitat quality and capacity, I selected the paper Can Stream and Riparian Restoration Offset Climate Change Impacts to Salmon Populations? This was written by Justice, White, McCullough, Graves, and Blanchard, published in 2017. So the author's main research question was, what are the potential thermal benefits of riparian reforestation and channel narrowing in the context of future climate change? And they're looking at this for spring and summer Chinook salmon populations in the upper Grand Ronde Basin here in blue, which is a major tributary of the Snake River in northeast Oregon, and the Catherine Creek Basin here in green, which is a tributary of the Grand Ronde. I will say for the Catherine Creek Basin, they were just looking at spring Chinook salmon. And kind of the justification for the study was this area has experienced a lot of land use practices that have reduced the streamside vegetation, so kind of getting rid of some of that shading, and it has also increased the channel width, which has ultimately led to higher water temperatures. And as climate change continues, there's a greater concern that these water temperatures will be over the optimal range for salmon growth and survival in these habitats. So this study was a model-based spatial and temporal comparison study. It's spatial in the fact that it compared two different basins, Upper Grand Ronde and Catherine Creek. Even though they're right next to each other, they still have all these different conditions like their water temperatures, their stream widths, their vegetation cover, etc. And then it's temporal or through time as well. It's a study because they're simulating their future climate conditions through the 2080s and seeing how that will impact water temperature. And so overall, their objectives were to, one, simulate the water temperature changes from restoration actions, and then evaluate if climate change impacts can be offset by restoration, and then ultimately predict how simulated temperature changes influence the Chinook salmon par abundance in these habitats, and then develop a tool for guiding future restoration projects and setting prioritization levels. So getting more into their methods now, the main chunk of it was this temperature model called heat source, which is used to simulate water temperatures and flow dynamics by using stream channel geometry, the hydrology, riparian vegetation cover and height, climatic conditions, to simulate stream temperature and effective shade at 100-meter intervals throughout the stream network. Um, and so some of the specifics of their inputs that they actually put into their heat source temperature model was the channel topography and which included things like the stream width and gradient. They also had riparian vegetation in there, obviously, which had the canopy height and density, and they got that data using LiDAR. Um, they also collected water temperature data, which is all of these triangles here using hobo loggers, and they were placed at the model boundaries and at confluences. They also obtained climatic data like air temperature, wind speeds, cloud cover from various sources like the National Weather Service and U.S. Forest Service like weather stations in the area. They obtained their stream flow input data from gauging stations on the study site and actually going out and collecting their own measurements as well. And then this one was a new one for me. It was this FLIR or FLIR infrared imaging, which is remotely sensed forward-looking infrared surveys. And they conducted these during the summer of 2010 to capture little snapshots of the peak daily water temperatures throughout the stream network. I guess I should mention also their stream network that they actually model is everything here in black. So this lower part of Catherine Creek, they did not model, which is a bias you might. So, and using these snapshots from 2010, the model was calibrated to those conditions they observed and also could adjust it by adjusting the model parameters to minimize the deviation between the observed and predicted water temperatures. So that's why it's so important that they're kind of using these hobo loggers to get known data to see how well their model is actually stacking up and comparing. So ultimately, this heat source will be their 2010 kind of baseline model of water temperature. Um, but then they also have to create these other scenarios where they're simulating riparian restoration, simulating channel narrowing, and then also simulating climate data to the 2080s. And they got the riparian restoration data from working with a team of riparian ecologists from going out into the actual study site and collecting data and then making estimates of what they would expect to see in the 2080s. And then for the channel widths, that was something they could adjust in heat source, which made it kind of easy. And then the climate change data for the 2080s they got from a climate data center in Washington. So I kind of talked about that baseline model there in the 2010s. That's what the water temperatures are currently. Um, but then ultimately, they want to see how just restoration alone impacts water temperatures, how climate change alone impacts water temperatures, and then how climate change and restoration combined impact water temperatures to see if that restoration will offset them. So they have these 10 different models here. I'm not going to go through them all, but obviously we have the current one. P and V is the potential natural vegetation. So what the stream side would look like if we didn't get rid of all of the vegetation and it was more shaded. And then they have these different restoration priorities. I'm going to skip over that for this PowerPoint because I've tried too many times and I can't get it in time. Um, but then they also have just alone the width for the channel narrowing. And then obviously down here, like I mentioned, combining that climate data with the vegetation and channel narrowing restorations implement. And so again, some of these biases that I noticed or that I kind of picked up on was the model extent, as I was talking about earlier, where they didn't do this lower portion of Catherine Creek, and they just kind of said it was out of the scope of their study. So that's something I think would be very useful to have. And also there's missing areas where the stream flow was too low during the summer. And I think another bias is they're only considering vegetation channel width as factors influencing water temperature when there can be plenty other factors that they could add into their models to better estimate water temperatures through restoration and as climate change continues. So getting into their data analysis a little bit here, they predicted the maximum weekly maximum temperature for all 10 of those model scenarios. We're just going to look at two here. This top one is the 2010 baseline current model. And then this bottom one here is just with the stream side restoration, the reforestation. And maximum weekly maximum temperature is basically what week in the year where the mean temperature is the highest. So we're trying to figure out what the temperatures will look like during the warmest parts of the year and how Chinook abundance will change during the hardest times for them. So as you can see in the current condition, it's pretty dang hot throughout the entire area where it's getting cooler up in the tributaries. But when you add in that potential natural vegetation where you're getting more of that stream shading, temperatures drop pretty much everywhere except for on the main stem, kind of Grand Ronde, lower downstream. And then the other thing they were looking at was linking that temperature data to Chinook par abundance. And to do that, they used a linear mixed effects model. And that is right here where we have maximum weekly maximum temperature on the X and the par density on the Y-axis, log transformed. And so as that temperature increases, par densities are going down. And their fixed explanatory variables they used to explain this was the watershed area upstream of the site gradient percent, or like the slope, how steep it was, the site maximum weekly maximum temperature, and then the average red density. And overall, they found that these explanatory variables accounted for about 51% of that explanation, which was their R squared value. So going into our, excuse me, our key results for the water temperature. Um, Here we have the maximum weekly maximum temperature on the y-axis and our different modeling scenarios on the y-axis. Um, Plot A up here is for the upper Grand Ronde Basin, and then B is Catherine Creek. As you can see, 0 is our current, so anything that's negative is going to be meaning the water temperature is decreasing. Anything up that's positive, water temperatures are increasing. So I want to focus at the end here. They found that with both restoration methods included channel narrowing and riparian reforestation, they found that that could drop the temperatures negative 6.5 degrees Celsius in the Grand Ronde and negative 3 degrees Celsius in Catherine Creek. However, when you extrapolate that data, not extrapolate that data, but just look at the climate data in the 2080s, they expect water temperatures in the Grand Ronde to go up to 2.7 and in Catherine Creek to go up 1.5 degrees Celsius. However, if we include these restoration scenarios into that model with the climate, they found that it can actually offset climate warming and drop the stream temperatures still from their current 2010 baseline data, which I thought was pretty cool. With the biggest effect being whenever they include the reforestation and the channel narrowing, especially for the Upper Grand Ronde. And then looking at the Chinook par abundance based on this data, on the x-axis, or excuse me, y-axis, we have Chinook par abundance in the thousands. Again, A is the Upper Grand Ronde, B is Catherine Creek, and then our x-axis, we have our different modeling scenarios. So here is our current 0. They found if we include both restoration methods from that 2010 current climate data, that they could actually increase Chinook abundance, Chinook par abundance by 590% in Upper Grand Ronde. But for Catherine Creek, it's still going up, but 67%. Whenever they're looking at just the climate projection, they expect a negative 53% drop in the Upper Grand Ronde and negative 36% drop in Catherine Creek. But when we combine that climate data projected out to the 2080s, but included with our restoration information, it would offset those declines in Chinook abundance and actually increase, with the biggest impact being seen on the Upper Grand Ronde with the channel narrowing and streamside reforestation going up 114% from our baseline 2010 current data. So some conclusions. Think they did a good job. They found that restoration can significantly reduce stream temperatures, which was one of their goals, and that the restoration can offset climate warming effects on juvenile Chinook habitat and therefore increase that Chinook par abundance. They also found that it would be a good basin-wide planning tool that could help practitioners prioritize what areas they should be focusing on and restoring. So overall, I think they met their goals. And it was a good study. So going into my personal assessment, I thought that the model was well calibrated and had reliable data sources. And I thought it was really cool that they were trying to relate water temperatures to par abundance. And it was nice to see that their results aligned well with other studies that did similar things in similar rivers, like the John Day River, also in Eastern Oregon. Some limitations I saw, though, was that they only implicitly accounted for par density dependence using red abundance. They didn't do a standard like Beverton Holtz or Ricker model. And the linear mixed effect model only explained like 51% of that variation in the Chinook par density. So clearly we're missing, well, almost half the picture of what's explaining that. And so some alternative hypotheses I thought about was that in-stream restoration efforts like log jams or beaver dam analogs may also buffer stream or buffer rising stream temperatures by creating thermal refugia or better rearing habitat with enhanced opportunities, therefore increasing sandbar abundance. And also flow restoration by like buying water rights, altering dam water releases, or improving irrigation, basically just trying to keep more water in the system can reduce water temperatures by increasing the stream's ability to withstand different heat loads. So here's the citation for my paper. Thank you all for watching, and I look forward to responding to your questions. Thank you.